Okay, so before the break, we were surveying discriminant analysis and how that worked. And we said that the t-test can be seen as kind of like a primitive discriminant analysis when you reverse things around. Okay. So what we want to talk about now is the multivariate analysis of variance. And the multivariate analysis of variance is abbreviated to MANOVA. Okay, so it's MANOVA. It's got a nova in the root, but it's got the M for multivariate. And the idea that we came across in the previous part of today's class was the idea of mean vectors. So we saw that mean vector statement, and we saw the equivalency of covariance matrices, which was fine. That was it kind of made sense, but the mean vectors definitely did not in the context we were working in. Well, this chapter in Stevens is all about mean vectors. So we're going to liken this procedure to the discriminant analysis that we just saw. Now, how that comes about, we're going to see. We're going to see the similarities as we go, and then we're going to see that they're basically addressing a very, very similar question, and there's a whole bunch of parallels between the two procedures. So let's start it off. We start off with the univariate t. Okay, univariate t is that population means are equal. So that's familiar. There's our univariate t. Now, when we go to the multivariate case, we have this hypothesis under the null hypothesis. That's the population mean vectors that are equal. Now, why do we need mean vectors? Okay, why do we need mean vectors? Well, let's draw the analogy to what we just did in discrim. When we did the discriminant analysis for p is equal to 1, that was analogous to univariate t, because we only had one predictor, so we were just dealing with population means. So p is equal to 1 is analogous to this situation here. We pointed that out before the break. We said this is a lot like the t-test, assuming equal variances and such, so there are similarities there. The multivariate case, where you have mean vectors, that's analogous to the situation of P2, P3, P4, etc. So you have greater than P is equal to 1. So you have 2, 3, 4, etc. Now, how does that work into it? Because these here are means on the given variables. Okay, so this is the mean on the first variable, this is the mean on the second variable, and this is the mean on the pth variable. So mu sub 1, variable 1, mu sub 2, there's the 2, variable 2, mu sub p. Mu sub p. They use the same notation here, thankfully. Stevens used the same notation. I keep referring to Stevens because he's the actual original author of this book. It's gone through a few editions, and this person just came on. I guess this person's assuming responsibility for the book now, but it's this book started off with Stevens many editions ago, so I'll just refer to it as Stevens. Plus, I'm not quite sure how to pronounce that name, so it's easier just to say Stevens. So P1, P2, P3, these are all those variables. Now, why do I have two vectors here? I have two vectors because we're looking at the two group multivariate case here. Okay. Pretty soon we're going to generalize that to having k groups. Instead of having just two, we're going to have k groups. So there's group 1, there's group 2 on several variables. So if I were to draw the function statement up here, again, the function statements help clarify a great deal. What do we have? We have y1, y2, two dependent variables, okay, two dependent variables in this particular case. So I'm just taking two variables, so that's like taking these first two. Okay, there's the first two there and the first two here, across a grouping structure. Group 1, Group 2. Where is the grouping structure represented here? There's one group, there's another group. Notice how this is the same idea as when we flipped it around and had X over here, 1, 2, and Y1, Y2 of the previous stuff we did before the break. The problem that we just looked at before the break was taking the P is equal to 2. That was the X1 and X2, to use the terminology that James was using, to predict or classify into groups. This was the problem that we just looked at. And we said this problem gets complicated because we have more than one predictor. We have more than one predictor. The reason why I'm calling this Y over here is because it's now becoming the dependent side, whereas before it was the independent side. Okay. So what we're actually doing is something very, very similar, but it's developed in a different way. And we're going to see, we're going to be interested in different things from it. But the mean vectors comes from the idea that you have one group here and one group here, and you're looking at means of Y1 and Y2 between those groups. That's why we need this vector idea. We no longer are interested in just the mean of Y1 across groups 1 and 2. We are interested in the means of Y1 and Y2. Vector, that's a vector, across groups 1 and 2. That's why we have this. How could I make this more complicated if I put in a third group? So if I put in a third group, let's say I have a third group here, what do I need to add here? That's a good way to kind of test, see if you're understanding this. Do I add more variables here? No, I don't have to. I just need another grouping structure right here. So my two variables here, Y1 and Y2, they could still remain the same, Y1 and Y2, but I'm going to add in a third group. So I've got, there's my third group there over here. Okay. I hope that makes some sense in terms of what this is actually evaluating and how it's similar to what we just did in the discriminant case. But in the discriminant case, we wanted to just do group classification based on the X1 and X2. But the X1 and X2 are the same thing analogously to this. So that's where that mean vector idea comes from. So when we're doing that discriminant analysis, there are mean vectors involved. It's just that we don't really want to study them. We're not interested in that question. In the discriminant analysis, we're not interested in looking at these mean vectors. It's not our hypothesis. In the analysis we did in the previous chapter, we just want to take those variables and use them for classification into X1 or X2. Okay. Now, again, I'm kind of, my notation's a little bit messy here because I keep like reversing situations. But I just want to make sure that's clear in terms of what we're doing. Let me just clarify it here because that is getting a little bit messy there. Y1, Y2, those are my dependent variables. There's 0, 1. This is the situation we're looking at when we look at this multivariate analysis of variance. We're going to start off with the two group structure, and we are predicting two variables simultaneously, which what that really means is we're looking at mean vector differences between these two variables. So you're going to have a mean of Y1 and Y2 in 0. You're going to have a mean of Y1 and Y2 in 1. And you're comparing those two vectors. Now, just so our notation doesn't get confused here, what did we just look at in the previous chapter? In the previous chapter, we looked at X on this side, 0, 1, and Y1 and Y2 on this side. There's that comparison. But the thing is we normally don't want to call this X in this particular situation. probably just want to call it y because it's the dependent side. Okay, so I called it x over here. You can just replace that with y and call these x's. I'm just trying to show how they relate to one another. The problem of the previous chapter was for P2, for that multivariate case, we're looking at two predictors predicting classification on the binary variable here. So remember that we had to assume equal covariance matrices, and that's where the mention of mean vectors was from the previous stuff on discriminant analysis. Now you see where those mean vectors kind of happen. Okay, we'll see the analogies, and we get over here, we'll see a lot more of those analogies. Okay, for now, let's develop this from this mean vector side. Now, the question too is, why would you want to combine these two variables together? Okay, why would you want to combine these two variables together? Well, we didn't need a rationale when we were doing discriminant analysis, right? We just said, hey, take x1 and x2, right, which is our y1 and y2 here, take those two predictors and see if they can predict group membership. We never asked, why are you choosing y1 and y2 in the same model? We never asked that question, right? So when we did this over here, right, when we had the two predictor case, x1 and x2, we never said, why are you putting x1 and x2 in the same model? Why are you analyzing those simultaneously? We never asked that question because in discriminant analysis terms, we don't really care. We're just trying to see if it discriminates between categories, right? So in this book, James, they're not caring whether x1 and x2 go together in some sense or whether they're meaningful. Why? Because the discriminant analysis that they're presenting here is kind of like atheoretical. They don't really care. They just care if they can predict bank fraud, or credit card fraud. Are you gonna conduct credit card fraud? Well, what are the predictors of that? And whatever those predictors are, we just care if we can classify you into the group of credit card fraud or not credit card fraud. So that question of x1 and x2 kind of going together or belonging together in the same model did not really make that much sense to ask. Here, however, it does make sense, and it's actually quite important when you're thinking about it in terms of MANOVA. So the question we want to answer is, why put y1 and y2 in the same model? Okay, so leave the discriminant analysis behind for a second and just think of it in terms of this multivariate ANOVA. Well, if I only have a single response, what do I have? Single response, binary independent variable, I have a t-test situation, right? I have a t-test because this is a single response and this is a binary independent variable. That's a t-test situation. Are there mean differences on y1 across 0 and 1? I could do the same thing for y2 and I'd have a t-test situation. Group differences on y2. If I added another group here, what do I have? y1 differences across 0, 1, 2. What is that? That's ANOVA. How about for y2? 0, 1, 2, that's another ANOVA. So the question we need to address here is, why would you want to put y1 and y2 in the same model? So why would you want to do y1 plus y2 together? Well, you should have some kind of theoretical rationale for doing that. That's the answer to that. Again, in the discriminant problem, we didn't care about x1 and x2. We didn't say, hey, why should they belong together? Very anti-theoretical in that presentation. But here it's all about theory because you're trying to predict or you're trying to model mean vector differences on these two things simultaneously across groups. So these two variables, you should have some kind of a theory as to why they should be considered in the same model. Otherwise, MANOVA makes no sense to do. Okay, it makes no sense to do. So we'll look at an example here as to why it may make sense to put them in to the same model, but those should go together. Now, the obvious example, or a common example is, maybe you're looking at quantitative and verbal ability. Quantitative is Y1, verbal is here. Well, those go together because maybe there's some measure of like kind of ability or functioning or something like that. So it kind of makes sense. But you should have some rationale as to why you're putting them in the same model. As Stevens discusses, you definitely don't want to put them in the same model just because you have two response variables. So, and sometimes researchers will do that. They'll say, well, how many response variables do we have? We have 3 or 4. Okay, put them in the same MANOVA. That's not a good thing to do because maybe they don't even belong together. Why would you want to analyze those two variables together if they're not of any theoretical meaning? So then you might ask, well, why not? Why not just analyze all variables all the time, and however many variables you have, just throw them into the model? Well, there you get to that bias variance trade-off. That's how you relate that stuff to what we just saw. Because if you include Y1 quantitative with Y2, how many times you go running per day? Well, those don't belong in the same model. And even if you get a fit on that model that's successful, it's probably not going to generalize to another data set, that type of thing, right? So that's why when we say theory should be your guide here, it definitely should. Otherwise, the MANOVA just won't make sense. So since we're dealing with a two-group structure, let's look at how the t-squared will develop. So this is going to be what's called Hotelling's t-squared for the multivariate case. So we're going to look at the multivariate version of the t-test. Well, to show this, we start off with univariate t. There's univariate t. Okay, so that looks familiar. There's our mean difference. There's our pooled variance term over here. Well, we're going to square these terms. Okay, we're going to square these terms because we're trying to develop something called Hotelling's t-squared. So we're going to square them. And we can rewrite some of this. We're going to play around with this equation a little bit. When we play around with this, look how we can write this term here. So you can see we're going to get things into matrix notation, right? So we've got this in the denominator. So squared mean difference divided by this. Well, what's the equivalent in matrix terms? Take the inverse. Again, that's what that inverse is saying. It's kind of saying like put that in the denominator. Okay, now technically the inverse isn't saying put it in the denominator. It's that analog to division though. So you're taking this mean difference multiplied by this inverse, multiplied by that mean difference. So you can see that we've separated our squared term, one over here and one over here. So we work through that and eventually you get to this formulation. Again, we're stemming from the univariate t, trying to develop this multivariate version, and this is what we get to so far. However, in the multivariate version, this is where things are going to change a little bit. So we've gone as far as we can to get this formula. But then we have to acknowledge that in the multivariate version, we don't have a variance. Right? We don't have a variance. What we have is a covariance. So we have a covariance matrix. We have variances and covariances. So this term, which is a variance in the univariate t, becomes the covariance matrix in the multivariate t. And these do not become mean values. They become mean vectors. They become mean vectors. This is just a term for n, not important. I mean, it offers no insight into the structure. So just consider that to be almost like just a multiplier that has to be included. But here's the crucial difference here. Mean vectors, variance covariance matrix. Okay, since we're likening this to the discriminant idea, this covariance matrix is the same idea that we talked about for why we needed x1, x2, x1, x2. This is the same idea that we just talked about. There's the cove and there's the cove. That's why we need this, because we don't just have variances. Okay, so again, I'm drawing that analogy to what we just did. Okay, so there's our Hotelling's t-squared. It's called Hotelling's t-squared because he studied this distribution quite a bit. And it's the multivariate analog to the univariate t. Okay. So an example here is really going to help. And the example here is with two group structure. So we have behavior modification, one group, and then we have cognitive therapy in another group. Okay. And then we have two response variables here. And I cannot for the life of me recall what these response variables are called, what these abbreviations are for, but just think of it as two variables that have some kind of relation to one another. In other words, the SA and the CSA are kind of similar to this idea of quantitative and verbal, right? They go together. They go together. If they don't go together and it doesn't make sense hypothesizing them in the same model, then don't do it. But in this case, they do kind of go together. So that's why you're wanting to include these in the same model. Otherwise, you shouldn't be doing MANOVA. You could just do a couple univariate analyses, right? So you got your grouping structure, behavior modification versus cognitive. Okay, so there's the group. People who are in the behavior modification group are not in the cognitive. You can just analyze the responses on SA. There's your one analysis of variance. It's a t-test in that situation. Think of it in terms of the ANOVA just for full generalizability here. But you can also do another t-test or ANOVA on the CSA. What's the MANOVA going to do? The MANOVA is going to look at SA and CSA together, right? It's going to look at it together, the X1 and X2, the Y1 and Y2, togetherness here. Simultaneously, are there mean differences on SA and CSA combined? So how are we going to analyze this data? How are we going to conceptualize this? Well, we see the null hypothesis is that the mean vectors are going to be the same. So again, what are the mean vectors? SA and CSA are the same across groups. Okay. Well, let's look at the comparison. T-test versus t-squared, the multivariate analog. Again, we're just dealing with the two group case here so far. We'll go to the K-group case where we have analysis of variance, but we have multivariate analysis of variance rather, but here it's just the two group case. But if you understand the two group case, going to the higher than two group case won't be hard. So let's look at how these things work. Well, we have to assume for the t-test, the within group population variances are equal. There's our familiar assumption. We even talked about that when looking at the discriminant analysis when I was trying to make the comparison already, right? It's called the common variance because we have to assume they're equal. You know, you're thinking like Levine's test to evaluate, you know, the null hypothesis that they're equal. There's our univariate. What's our multivariate? Well, the multivariate is that the within group population covariance matrices are equal, called the common covariance matrix. Do you remember what James was talking about? The common covariance matrix? It's the same thing here. We're just looking at it from a different perspective. So we have to assume that these covariance matrices are equal. Look, if they're not equal, in the discriminant analysis problem, you might want to consider quadratic discriminant analysis. Hope that kind of analogy is useful. If it's not, I'll recap this next week as well, because those ideas can actually be, they can be difficult to see how the two procedures are related to one another. Okay, and oftentimes I'm teaching this, I teach them as completely separate first, and then I relate them. Here I'm trying to do a little bit more of the relating as I go along, because we're combining a chapter from Stevens and the other book. And the other book does not mention the MANOVA idea at all. So I'm just letting you know where I'm actually getting that idea from the discriminant discussion, the common value. In the univariate T, we calculate the within group measure of variability. We pool the estimates. So you got sums of squares in one group, sums of squares in another group, divided by degrees of freedom. There's your pooled estimate term. If you think of that in terms of the wider ANOVA context, so if this became an ANOVA, so with a third group, this is basically saying what your MS error term is going to be, because you're taking your sums of squares dividing by degrees of freedom. Well, what's the analog in the multivariate situation? The analog is take W1 and W2, because it's a true two-group situation. Again, be very careful to note that the W1 and W2 is not referring to the fact that we have two dependent variables. It's referring to the fact that we have two groups in this case. Okay, I hope that's clear. Where's the idea of 2, 3, or 4 dependent variables in this? It's within each matrix, right? It's within each matrix. So I'm going to get a W1. That W1 is going to be Y1, Y2, Y1, Y2 for our particular problem, because we have two response variables, right? If I had a third response variable, I have Y1, Y2, Y3. But I would still have Y1 and Y2 because it's a two-group structure, right? It's a two-group structure because I'm only comparing cognitive to behavior modification. So it can take a while to kind of untangle that, because you see the W1, W2, you say, all right, yes, I've got two response variables. I've got two dependent variables, but that's not what the W1 and W2 are referring to. It's referring to the group structure. It's within each matrix that you're going to have those response variables. So theoretically here, if I chose to do something like analyze 10 response variables simultaneously, which would be a very bad idea, but let's say I chose to do 10, then I'd have Y1 to Y10. And I'd have a whole bunch of variances and a whole bunch of covariances along those variables. And those would all be variances along here. So I hope that's clear. How do you pool it? Well, you just add them up and you get your pooled estimate of the covariance matrix. This is S, so it represents for our sample. This is the estimate of the population covariance matrix. As usual, we don't care about the sample variance over here. We never cared about the sample variance. What we cared was whether it measured the population variance. Well, here's the same idea. We don't care about S. We really care about that population covariance matrix, which we're going to assume is going to be common to the different populations. Okay. So what does that mean in terms of our example? In terms of our example, that means that the covariance matrix between SA and CSA, SA and CSA, that covariance matrix is the same for behavior modification as it is for cognitive. Because you have one covariance matrix and you have another covariance matrix here. That's what we want to assume is true, that they're going to be a common covariance matrix. And again, you relate that back to what we just talked about in Discrim, and you might see those relations, because we had to do the same thing in the other one too. We had to assume equal covariance matrices. So what is our output? Well, actually, let's do the computation here. See how this is computed. Our null hypothesis in this case is right up here for this particular data. Two groups, one group, another group, right? So we assume that behavior modification is equal to cognitive. Now we've got two response variables, mean of one, mean of another. SA and CSA equal across groups, but we need the vector notation because of those multiple response variables. That's what that HO is communicating. So if you can relate this to this data and see why that's formulated that way, you're definitely understanding how multivariate analysis of variance works. And what you can do to kind of test yourself on this, and the assignment will test this as well to kind of see if you got your bearings in terms of what's going on here, is practice adding another vector. So add in the third vector. What changes here? Right, so just add in another vector. Go like another one. What changes? If the answer is, well, add in another one of these, that's incorrect. What changes is you've added in another group. Behavior modification, cognitive, nothing. This is the nothing group as the, say, the third group. Okay. Add in another dependent variable or response variable, and you're adding another mean down here. Okay, you're adding another mean. So you get another mean, another mean, another mean, depending on how many response variables you have. And that's one way to kind of see if you're understanding that idea. Okay. Okay, so what do the computations look like for this? What do the computations look like? Well, let's look at sums of squares sub 1 over here. Now, look at, you just look at the numbers and you see what's going on. 1 minus 2, so there's 1 minus 2 plus 3 minus 2, there's the 3, again the 2, plus 2 minus 2 is equal to 2. So what have we done? We've computed the sums of squares for SA, variable 1, in group 1, right? We've computed the sums of squares for this particular situation right here. Let's do it for the next one. Okay, let's do it for the next one. You're going to have 3 minus 4, 3 minus 4, plus 7 minus 4, etc., and you get the sums of squares for group 2. Now, all of this is still within the behavior modification group. Okay, so what we're computing here is still within behavior modification. Here's where multivariate analysis differs from univariate, because now, instead of just having two sums of squares, we actually have a cross product as well. So look at what this next term is. Take 1 minus 2, same thing here, the 1 minus 2, times the 3 minus 4. Look, 1 minus 2, cross it with 3 minus 4, right? 1 minus 2 by 3 minus 4. You can see what's going on because that's how you start to compute covariances. It's the crossing. Now you're interested in the relation between SA and CSA, and that's what's going on in this term. Do the next one, 3 minus 2, which we did here, times multiplication 7 minus 4. 3 minus 2 times 7 minus 4, etc., until you get that crossing term. So we call this the sums of squares and cross products matrix for group 1. You input these values here, and you get that sums of squares and cross products matrix for group 1. W1 is for behavior modification. This whole thing is for the behavior modification group. You have two dependent variables within that group. That's why it's called the within. And again, it's analogous to what happens in univariate. It's just more complicated. What makes it more complicated? What makes more complicated is this, because now you're doing the cross variation. You're not just looking at the sums of squares values. You know, if you want to think about it, all of this is univariate. This is univariate. This is where multivariate comes in. It's the crossing because you're relating those two variables. So there's for group 1, there's for group 2. So what do? We pool it, which is what we would do if we were pooling it in a t-test situation, right? In a t-test situation, we would pool variances as well, right? That's why you're looking over here. We're doing the pooling, and then we get our overall sample covariance matrix. And the sample covariance matrix is a pretty good estimator of that population covariance matrix, which is what we really want to know. So that's how that looks over there. The next step is not very not very enlightening. We just apply the Hotelling's T that we developed. So we're trying to see if there's mean vector differences. Well, we're going to need the inverse of S, right? Why are we going to need the inverse of S? We need the inverse of S because it's over here. Right? There's the inverse of S. So we need the inverse of S right there. We compute it, and then you put in those numbers, and you get 21. And this is just how you can evaluate the statistic. Many inferential or test statistics are related to one another. So, when you're computing like a T, you can relate that to an F distribution and et cetera. So this is just the details on how to get the F from the T squared. And then you evaluate that for statistical significance. And then you see if there's evidence to reject that null hypothesis. So we're into familiar territory once we get up here. Just note that it's about this hypothesis and not about a univariate analysis. So are there mean differences? Well, if you get a statistically significant result, let's say P is less than 0.05 or what have you, then you have evidence of what? You have evidence to reject this hypothesis, right? Reject this hypothesis, so you have an inequality of mean vectors. So mean vector 1 does not equal mean vector 2, a two-group test. Okay. So if we look at some output here, we see the multivariate tests are right over here. And there's the effect, so there's the group. So there's two groups here. We see a variety of tests. I'll mention those a little bit later as to why we see so many different tests, but we're looking at multivariate statistical significance here. So this is on the combination of variables, on the combination of dependent variables, are there mean differences? And in this case, all tests are reporting p-values that suggest there are differences. What do we see below here? We see univariate tests. So here we have the multivariate up here, and here we have the univariate tests for each response variable, each dependent variable separately, y1 and y2. Now, why would you want to do these tests? Okay, we started off with a multivariate hypothesis because in our example, we want to look at like quantitative and verbal in the same model, right? So, we did Q and V together, right? So this is y1 and y2 across the grouping structure 0, 1. So that's what this multivariate test that we just conducted is evaluating. However, you might also want to look at this hypothesis too, just y1. Well, that's what y1 is doing right here. You may also want to look at this right here, which is y2. That's what this here. So when you get to the test of the between subjects effects, you're into familiar ANOVA territory. You're just separating your response variables. The question is, why would you want to do this if your interest was doing the multivariate test? Okay. Now, we have to mention something here, is that it's entirely possible that these come out to be statistically significant in terms of your univariate test, but this one doesn't. Likewise, it's entirely possible that you get multivariate statistical significance, but you don't get the same kind of univariate statistical significance. Okay, and there's a name for that. It's called Rayau's paradox. And that can actually happen when you do your analyses, that the multivariate comes out, but the univariate doesn't, and vice versa. The reason for that is simply because of the way the covariance distributes itself across the variables, that sometimes one test can have more power than the individual tests. So you might see things like that. I mean, when you look at these p-values, notice the p-values are different from the multivariate test. What would be incorrect, and this is where I mentioned there's a few parts in Stevens that I'm going to kind of just comment on. The one part in Stevens seems to suggest you just do your multivariate test and then break it down into univariate tests. It's not quite like that, because we can find those different statistical significance values across tests. You can do the univariate tests, but I wouldn't look at these as kind of breaking down the multivariate effect. I would look at this as a separate hypothesis and these as separate hypotheses. That's the best way to look at it, because this is a different test. This is a different model, right? When you look at what we know from looking at regression work is that when you do Q and V, that is model specific, right? That's model specific. So if you decided to do something like this, talking about variable importance, right? Because the variable importance is such a big idea here. It's a big idea in regression, and it's a big idea here. If you looked at it Q and V and you said, well, I want to know which variable is most important, right? Is it Q or is it V? Well, that's pretty hard to determine here because they test different hypotheses. When you do Y1, you're just doing Q on X0, 1. It's not in the company of V, so it's a different model. This principle that we're talking about is analogous to the regression principle where, I keep saying that this relationship is different than X1 and X2 on Y. So don't interpret univariate effects or bivariate effects in the context of a multivariate domain. If you want to do X1 predicting Y, then do it, but that's a separate model, right? That's a separate model. This is a separate model than X1 and X2 predicting Y, than the multivariate idea. Okay, again, realize I'm just drawing the analogy. This isn't the analysis you're doing up here. I'm just relating it to what we've talked about in regression, where in regression, keep saying that we're testing different models. So interpret within the model. Always interpret within the model. So you can do your univariate tests, but if you're so anxious to do the univariate test, you may actually wonder why you did the multivariate test. So there's nothing wrong with doing it. Just treat them as separate hypotheses. Don't treat them as like a breakdown in that sense. Separate hypotheses, because of that covariability idea. Okay, so there it is for Hotelling's t-squared. I think we're going to stop here because I think that's enough stuff for today. And just let you know where we're going is next week, we'll just finish this off real quick before getting into the next chapter in James. And this is going to be the K-group MANOVA. So what we've looked at over here is we've done Hotelling's t-squared, where you had the two groups on that combination of variables. And then we're going to go into the several groups, and we're going to see how this is the full MANOVA model. And this is going to be likened to the analysis of variance, only that you have multiple DVs. Now, I just want to conclude today with kind of like a bigger picture thought of relating the discriminant to what we've been doing in this second half of the class, because we are going to have to develop this a little bit more next week as well. So I'm just going to put my Y1, I'm going to write this in MANOVA context, and we are just going to put the two group structure. Okay, so what have we done so far? Well, in the second half of the class, we've been looking for mean vector differences across the two groups, right? Mean vector differences across the two groups. In the first part of the class, this was flipped around, right? So we had the binary variable on this side, and then we had the two predictor values, right? P of 2 on this side, right? And now we're seeing that the problems are kind of the same thing. We're just asking a different research question, right? We're asking a different research question. So if I put this in terms of, I'm repeating what I said earlier, but you can't see this enough to kind of get the idea of what's going on with this. Y1 and Y2, there's our discrim. There's the discrim. There is MANOVA. Hotelling's t squared, but the generalization, which we'll develop next week, is the MANOVA. It's the full multivariate model. Here's something to think about for next week. In the James text, okay, in the first text, they're doing discriminant analysis, and we've surveyed what discriminant analysis is trying to predict the class membership. But at no point in the James text are they asking the nature of this linear combination. So this is going to be the linear combination. Remember at the end of the previous class, I said you're going to have a linear combination when I was talking about the MANOVA idea. Well, I'm going to have y1 plus y2. That's how this is going to be constructed. And this is going to be a scalar associated with y1 and a scalar associated with y2. So what I'm actually generating here is a new variable. I'll just call it L for now, which is a linear combination of y1 and y2. That's what this is doing. Linear combination of y1 and y2. Here's my binary variable. So what the discriminant analysis is doing is it's determining an optimal linear combination of y1 and y2 that separates these two groups. Okay, so I repeat that. This is going to be an optimal linear combination. Now, what do you mean by optimal? I mean it provides maximum separation between these groups. It provides maximum separation, between these two groups right here. That's what's actually going on in the discriminant analysis, is you're selecting scalars to weight that linear combination. And then it's reducing down to one thing, one linear combination. Now that's not mentioned in the James text. That's not mentioned in the James text. They don't talk about the nature of this particular thing that you're making to do the discrimination. So the easiest way here is to go right back to what we're talking about. And when we're talking about this idea here, right, you had x1 and x2. This is for a 3-group problem, but it's, we still have x1 and x2. They're not talking about the nature of x1 and x2. They're not talking about what scalars were needed to weight x1 and x2. Whereas over here, we are talking about that. Those scalars exist in the James text. They're just not showing them to you because they're kind of writing in the spirit of just classification. They just want to classify things. They're not telling you about that underlying function and this idea here, but we need to develop this idea because it's going to be prominent in the MANOVA that we'll talk about more next week. So just to summarize what we're talking about here is that when we do a discrim or when we do a MANOVA, there's a linear combination of these variables that is being developed. Okay, linear combination, each variable is weighted by a scalar. That's what's making it a combination of variables. So the question becomes here, what's this linear combination, right? What's this linear combination that's providing separation between these two things, between these two groups? Well, this linear combination is on this side in the MANOVA. Okay. So you can think of the MANOVA as being a linear combination here and then looking at differences between groups. That's another way of thinking about it. You think about it in terms of mean vectors, or you think about it as some kind of a linear combination that's different here between the two groups. Because from the discrim side, we're asking, hey, what's the linear combination that best separates the groups? That provides maximum separation. So there's 0, 1. You're trying to find a linear combination that provides maximum separation. That's the idea. And that linear combination is the discriminant function. That linear combination is the discriminant function that provides maximum separation. In MANOVA terminology, this linear combination exists, but we're not talking about it in terms of providing maximum separation. we're talking about as mean vector differences between the groups. But the problems are basically the same thing. They're just posed in different ways. And just to conclude, that's why when we go back over here, wherever that was, I can't quite find it. Wherever they mentioned it's right over here. There it is. That's why when they said here, with p equals 2, with a class-specific mean vector, a class-specific mean vector. What are the classes? Well, the classes are those levels of the independent variable in the MANOVA. Okay, I'm going to repeat that. These classes here are what we just looked at in terms of that Hotelling's t-squared, where we had two classes, and we had a mean vector in one class and a mean vector in the other class. That's the only place in this book where they give you the hint of the MANOVA here. And again, why do they not develop the MANOVA? Partially for historical reasons, that in the type of literature that this book is talking about, people really don't care that much about MANOVA. They care about the discriminant analysis idea because they're trying to classify, who's going to get COVID and who's not. But in a lot of psychology, at least historically, this MANOVA problem has been of fundamental interest because it is of interest to see if there's mean differences on a combination of variables, like the verbal and quantitative idea, right? So this whole thing, if I call this verbal, quantitative, maybe I add in another variable like analytical. I'm giving a bad definition of IQ here, but let's say that this here is some kind of a construct, right? I've just made the construct a little bit more complicated by adding another variable. And maybe I decide that that construct, like a good name for it, is IQ, right? Some type of IQ. So I'm interested in looking at this construct idea across levels of my independent variable. Last thought to think about, and then we'll end for today, is even if you just have y1, you're kind of doing something similar, right? Because y1, however you're measuring y1, is kind of like a construct as well. It's just a simpler construct, or it's a construct that's just being assessed with one variable. So let me just close with this. Here, we may choose to measure IQ with verbal, quantitative, and analytical. Maybe in another model, another researcher decides they don't want to do it that way. They want to measure something else for IQ, or they just want to do this: verbal plus quantitative plus analytical is how IQ is going to be measured in that model, and they just add them up. And when they add them up, that's what Y1 is going to be. Okay, so you see the similarities here, that when we do analysis of variance, that response variable, you could think of it as in terms of being a construct. Right? In terms of being a construct, it's just that what the MANOVA model allows us to do is elaborate on the number of observed variables. So maybe we can make it a little bit more complicated and combine them in such a way, right? Not just combine them like this is just adding them, but combine them in such a way that we have ideal scalars that will maximize the mean vector differences, or in terms of the discriminant analysis terminology, maximize group separation. And what we've just talked about in this last 15 minutes, again, is that overall idea of what's going on between these two models. The James text focusing on discrim. What we were just looking at in this chapter is focusing on MANOVA. And the details are different in each procedure, but we see we're actually doing something remarkably the same, just it's kind of discussed in different terms. Next week, we will go over this. We will go over this. So again, this is not an easy thing to get, how MANOVA and Descrim necessarily relate. So this will take a couple times to look at, and I will start next week with looking at this stuff over again and summarizing this idea and even retracing the Descrim to the MANOVA idea, and then we'll talk about the full MANOVA model here. And after we're done this, we're going to get back into the James text and look at resampling techniques. But we'll continue this next week. And that's it for this week. So see you next time.